Hello students, welcome you all. So in UV visible spectroscopy, today I will explain the types of electronic transitions. So we know that after absorbing the UV visible light, the electrons get excited from the lowest electronic state to the or from ground electronic state to the excited electronic state, or we may say that electron get excited from highest occupied molecular orbital, that is HOMO, to the lowest unoccupied molecular orbital, that is LUMO. So depending upon the types of electron involved, like suppose if sigma electrons or pi electrons or non-bonding electrons, the electronic transitions can be represented. So it can be represented by this diagram. Suppose if this we know that the sigma electrons, having the which is the most strong bond, sigma bond, most strong bond, or we can say most stable bond, so having the lowest energy, and then we may the energy level of this pi bond or pi electrons, this is sigma, and then this non-bonding, and then we may represent pi star, that is anti-bonding, and sigma star anti-bonding. So this is the energy levels. Okay, so sigma bond being the strong bond or stable one, having the lowest energy, then pi, and then non-bonding, most loosely held electron in comparison to this pi bond. So like this we can represent the energy level in this way. So different kinds of electronic transitions that may be possible is the sigma to sigma. One of the electronic transition possible is sigma to sigma star, and then or another like pi to pi star, or another electronic transition that is in may be possible n to pi star or n to sigma star. These are the possible electronic transitions. Now, if you will see this is the molecular orbital, sigma molecular orbital, pi molecular orbital. So, if we can represent this sigma molecular orbital in this way, the sigma molecular orbitals, we know that it is represented in this way, and this is our, and this pi molecular orbital, it can be represented in this way. Upper lobe have the positive sign and lower lobe is having the negative sign, non-bonding orbitals. Okay, and then the corresponding to this pi star, we can represent it at like this. This is upper lobe has the opposite sign, and in the same way like this. And sigma star that is non-bonding, okay, we can represent it, this is plus and this is minus. So as the no electrons are present between the bond, so we can represent in this way. The electrons are present between the bond, so electron clouds can be represented in this way. Okay, so why, one of the question arises, why the sigma to pi star is not allowed. I have not represented the sigma to pi star transition. Okay, and I have also not represented pi to sigma star. So these two transitions, if we see in sigma to pi star, I have not represented this one. In the same way, pi to sigma star, this is also not represented in the figure. So the reason that we may explain behind this, that if you will see this sigma molecular orbital, then sigma molecular orbital is the symmetric one. Sigma molecular orbital is the symmetric molecular orbital, and suppose if you see, we can explain it by the concept of Girard and non-Girard also. So one is the Girard, G, that is Girard, Gerade means orbitals having the center of symmetry. So gerade means orbital having center of symmetry. Okay, and whereas non-gerade or ungerade orbitals, it is represented by U, and this is orbitals having no center of symmetry. No center of symmetry. So if you will see the sigma molecular orbital, then sigma molecular orbital is the symmetric one. If you see from center, if we go in opposite direction, both is having the plus plus, we can say both is having the plus plus. So this is the gerade one. This is the symmetric orbital. Now if you will see pi molecular orbital, then from center, if we go in a opposite direction, then what you observe, we are getting plus and minus sign. It is non-symmetric one, and it is represented by U. It can be represented as a U. Now pi star, from center we get the, if we move in the opposite direction, both sign is same. So this is the symmetric molecular orbital. That's why you can say this is G. And this is again in the center. If we go in opposite direction, we are getting opposite sign. That's why it is non-symmetric, or it has no center of symmetry. So that's why it is a ungerade. So what you have seen, one of the possible transition from sigma to sigma star. So sigma is gerade and this is ungerade. So always the transition is from either symmetry to unsymmetric or non-symmetric, or from non-symmetric to symmetric one. So when any transition occurs, then the symmetry will change. Either the symmetry will be changed into non-symmetric, or if non-symmetric can get changed into the symmetric one. So during transition this will take place. So here the symmetric one is changing into the non-symmetric one, and in the same way, if you will see pi to pi star, this pi to pi star, the unsymmetric is changing into the symmetric one. So that's why the transition is taking place. So if you will see sigma to pi star is not possible. Sigma to pi star is not possible because this sigma is, as you can see, sigma is gerade one and pi star is also gerade. So both are, this is gerade, this is gerade. That's why from when the transition takes place, then symmetry changes. So here there is no change in symmetry. That's why it is not possible. In the same way, pi to sigma star is not possible. Pi to sigma star is not possible because both are ungerade, both are non-symmetric orbital, and if transition takes place, then symmetry changes. So that's why this is also not possible. So these are the possible electronic transitions. So let us discuss one by one. And so one is the sigma to sigma star transition. Okay, first one is the sigma to sigma star transition. So where it will occur? So it will occur because it takes place where the sigma electrons are involved, or single bond is present, where single bond is present and they are found in saturated hydrocarbon. They are found in saturated hydrocarbons, or we can say this like alkanes. They are found in alkanes. So suppose if we have a C single bond C, and if the bonding electrons, I represent the bonding electrons in this way, then after this sigma to sigma star transition, so one of this electron which is present in bonding molecular orbital, one electron will go into the anti-bonding region. So either another electron can go here or here, which is the anti-bonding region, or we can say the anti-bonding orbital. So we can represent the sigma to sigma star transition in this way. Okay, so this transition, if you will see, this transition requires very high energy. One of the things, it requires very high energy. It requires very high energy. So why very high energy? Because the sigma bonds are very difficult to break. That's why it requires very high energy. And it means it falls into the UV region. And you know, out of this UV and visible. So what I told you, this UV, it is from around 190 to 400 nanometer. And whereas visible, it falls in the range from 400 to 800 nanometer approximately. So this UV region is the high energy region, so when high energy is involved, when bonds are a very strong bond, then to excite the electron we need a high energy. So it requires the high energy, and sigma to sigma star transitions falls under the UV range. Okay, so after absorbing the UV light, which is the very high energy light, so what may happen that what I told you, such type of transitions, if you want to study such type of transitions, then they can be studied under vacuum region. So in the UV, that is vacuum region. So it is found in okay, vacuum ultraviolet region. And as it is found in, it means the to study such type of transitions, we need a vacuum arrangement in the UV visible spectrophotometer. Otherwise, what will happen? The oxygen which is present, the air which is present in the surrounding, and that will also absorb this UV visible light, and we can get a band due to the this oxygen absorption, or from nitrogen also. So nitrogen or oxygen can also absorb high energy, so much high energy. That's why we need a vacuum. So instrument requires vacuum arrangement. So that oxygen O2 does not absorb high energy UV light. Okay, this is the reason. So what I told you, they are found in a saturated hydrocarbon. Such type of transition occurs in a saturated hydrocarbon like alkanes. So for example, CH4, or we can say C2H8, that is ethane, or this cyclopropane. If you say cyclopropane, it is also a saturated one, that is C3, this is, sorry, C3H8, suppose this is C3H8, and C3H6, this is the cyclopropane. So now, so out of this, cyclopropane being the cyclic one, this is a cyclic one, and these bonds are quite strained bonds, so it can be easily broken down, and it requires less energy in comparison to, so here this sigma bond, these sigma bonds require less energy in comparison to the CH bond, or the CH bond here, or we can say CC bond. So sigma bond here, this requires less energy. So means the less energy means high wavelength. So if you say from here to here, the lambda max here decreases, and lambda max increases from an energy energy decreases. So as it requires less energy, it means it requires a high wavelength. So this is now in the same way we may explain the another transition, like suppose n to like n to sigma star transition. So suppose n to sigma star transition. So it is involved where it is possible, where these n electrons are present, non-bonding electrons or lone pair of electrons are present, and single bond is involved also. Okay, so for example, means one of the heteroatom should be present. Okay, in a molecule heteroatom should be present, and heteroatom that should be better, it is linked with some single bond. For example, this alcohol, you can say that this is a heteroatom, and this non-bonding electron are present, and this is the sigma bond which is present. So here n to sigma star transition is possible. In the same way, this like alkyl halides, or suppose this is present, or are NH2 these. So it is they have a this non-bonding electrons. So that's why n to sigma star transition is possible over here. Okay, so n to sigma star, as you can see, n to sigma star require less energy in comparison to sigma to sigma star. So as this n bond, that is a lone pair of electron or non-bonding electron, are the loosely held electron, that's why it requires less energy. Okay, so they are a very strong bond. They are not loosely held electrons. The sigma electrons are not loosely held electron. It requires the high energy. So it requires less energy. It requires less energy than sigma to sigma star transition, because n electrons are loosely held electrons. So this is the reason. Okay, so we can represent it in this way. Suppose if we have alkyl halide and n electrons or lone pair of electrons are present over the this halogen atom. So after absorbing the light, n to sigma star transition is possible. So we can say that one of the electron will get excited from the non-bonding orbital to the sigma star, that is anti-bonding sigma orbital, and we may represent this like this. Suppose these are the, as it contains the three lone pair of electron, one electron remains over here, one of the electron will get excited and it will go somewhere in a non-bonding region. So either it may go over here, we can write over here. So one of the electron will go into the non-bonding region, like this we may represent it. Now, suppose if we have a alkyl halide, like if we have CH3 alkyl chloride and alkyl iodide. So out of these two, which will requires the higher energy? Which requires the higher energy out of these two, or which have the high lambda max value? So the bond which is the strong, means where the n electrons are not easy to get excited, in which case. So we know that this chlorine is more electronegative in comparison to the this iodine. So that's why in this chlorine the lone pair of electrons are much tightly held. So they are not easy to get excited. So it will require high energy, means low wavelength. So here the wavelength is less. So here the wavelength is less, wavelength is high. So why wavelength is less? Because energy required is high over here. So energy required is high. Energy required is high in this case, and wavelength therefore is less wavelength. In the same way, suppose if we have methyl alcohol, and suppose if we have triethylamine, if we have a triethyl or triethyl, okay, if we have trimethylamine. Okay, so now out of these two, which will require the high energy or low wavelength? So we can see this oxygen which is more electronegative than nitrogen. That's why to excite this non-bonding electron in oxygen is much more difficult in comparison to nitrogen. So this requires the high energy, that is wavelength, low wavelength. Now, one of the questions that suppose if this trimethylamine, if it is present in acidic medium, then one of the question is that it doesn't show the N to sigma star transition. So one of the question that in acidic medium, trimethylamine does not show N to sigma star transition. So what is the reason? So in acidic medium, triethylamine does not show any N to sigma star transition. So one of the reason maybe means this N electrons are not available in acidic medium. So we can explain that is N electrons are not available. So suppose I write this one in acidic medium in presence of H plus, what will happen? So it will go here and it will form this bond. So that's, as you can see, the N electrons are not available in this case. So as the N electrons are not available, that is N electrons are not available in acidic medium. That's why it will not show the N to sigma star transition. Now, next transition, that suppose this pi to pi star transition. Okay, pi to pi star transition, and such type of transition, they are found in a molecule having the pi bond or multiple bond. So okay, so this is pi to pi star transition, where it is found. Such type of transition, they can be found in multiple bond, like in double bond we can see, in triple bond, or also in some aromatic compounds. It can be found, or suppose this carbonyl compound, where so in this carbonyl compound or in this imine, such type of transitions where double bond is present. Okay, where double bond is present, like double bond between this nitrogen and oxygen, this can be found out. So now this transition is these transitions are possible in this one. Now, so suppose if we have we can represent this one like this. Suppose double bond is there, and this one of the pi bond I have represented in this way, and after absorbing the light, pi to pi star transition will take place. Okay, and one of the electron will get excited from pi molecular orbital to the pi anti-bonding, pi bonding molecular orbital to pi anti-bonding molecular orbital. So here one electron and another electron, I can show the another electron in this region, anti-bonding region, or in this region. Suppose I write it over here. So one of the electron is going into the anti-bonding region. So suppose if we have ethene, and then we have now I have this butadiene, and then I have hexatriene. Okay, so in these three molecules, one of the pi bond is increasing. There is a conjugated pi bond in butadiene and one more conjugated pi bond over here. So as the conjugation increases, the lambda max value increases. So here lambda max value increases here. Or we can say the energy required to excite the electron decreases. Energy required to excite the electron decreases in the more conjugated molecule. Okay, so it means if energy required to excite the electron decreases, means the energy between this HOMO and LUMO decreases. Energy gap between the HOMO or LUMO decreases. So in this case, and that is we can say the energy gap between HOMO, highest occupied molecular orbital, and lowest unoccupied molecular orbital decreases. So this is the reason that this absorbs at the higher wavelength in comparison to this. Now we can represent this one in this way. Suppose this is non-bonding one, and then okay. Now, so suppose if we have a ethene, then as in ethene, how many p orbitals are there? The 2 p orbitals are there in ethene. If you will see, and 2 p orbitals are present in ethene, and these 2 p orbital, they overlap to form a pi bond. So as 2 p orbitals are involved, or 2 p atomic orbitals are involved, so number of molecular orbital formed, that will be 2. So same number of molecular orbitals are formed after the combination of atomic orbital. So 2 p atomic orbital combined to give 2 molecular orbital in case of ethene. So these are the 2 pi molecular orbitals. Suppose I write it pi 1, and this is, suppose this is pi and this is pi star. Okay, so in case of ethene, 2 pi molecular orbitals are there. Okay, pi in pi star, and 2 pi electrons are also present in here. So 2 pi electrons that will be filled in pi molecular orbital. I should fill the this 2 pi electrons in pi molecular orbital. This is the bonding or molecular orbital, and this is the anti-bonding molecular orbital, or we may say that this is the highest occupied molecular orbital, and this is the lowest unoccupied molecular orbital. So this is the HOMO and this is the LUMO in case of ethene. So what I told you, as we go from ethene to hexatriene, the energy gap between HOMO and LUMO decreases. So this is the energy gap. This is the energy gap between HOMO and LUMO in case of ethene. Now, if we see for butadiene, so in butadiene, how many pi molecular orbitals are involved? So how many p orbitals are involved in butadiene? 4 p orbitals, 4 p atomic orbitals are there in case of butadiene, or 4 p orbitals are involved in a butadiene, and they combine to give 4 pi molecular orbitals. So in case of ethene, I have written 2 pi molecular orbitals. in case of butadiene, we have 4 pi molecular orbitals. So 4 pi molecular orbitals I may represent like this, 4 pi molecular orbitals in case of butadiene. So this is our butadiene, and suppose this is pi 1, this is pi 2, pi 3, and this is pi 4. Now, how many pi electrons are present in butadiene? 4 pi electrons are present in butadiene. So I should fill the 4 pi electrons first, this lowest molecular orbital, then this highest molecular orbital. So this is our HOMO in case of butadiene, and this is the lowest unoccupied molecular orbital in case of butadiene. So now if you will see the energy gap in case of this butadiene, energy gap between HOMO and LUMO is this. This is the energy gap, and which is less than that of ethene. Okay, so that's why here energy gap decreases, and so it will require higher wavelength in comparison to the ethene. In the same way, for hexatrine, if you want to represent for this hexatrine, 1, 2, 3, 3 pi bonds are there in conjugation with each other, and if 3 and how many p orbitals are involved to form this 3 conjugated pi bond? 6 p orbitals are involved to form this 3 conjugated pi bonds. So if 6 p orbitals are there, then number of molecular orbitals formed, that will be 6. So 6 atomic orbital combined to give the 6 molecular orbital according to the molecular orbital theory. So we can represent it in this way: 1, 2, 3, 4, 5 and 6. So suppose I write it pi 1, this is pi 2, 3, pi 4, pi 5 and pi 6. And how many pi electrons are involved over here? This 6 pi electron. Now I can fill the molecular orbital by this 6 pi electrons. So 2 pi electrons in the lowest molecular orbital, next 2 pi electrons in this pi 2, and next in this pi 3. So this is the highest occupied molecular orbital. Pi 3 is the highest occupied molecular orbital, whereas pi 4 is the lowest unoccupied molecular orbital. So as you can see, the energy gap between these two, delta E, this is the delta E. Energy gap is delta E. Okay. So in case of hexatrine, the energy gap is the lowest energy gap is present, and that's why it requires the high wavelength. So as the conjugation increases, the energy gap between HOMO and LUMO decreases and the lambda max increases. Same thing I have explained in my previous lecture for the color and conjugation. So as the conjugation increases, the color also increases. So one thing for this pi to pi star transition is that the epsilon naught value is very high, or we can say the molar absorptivity or molar extinction coefficient for this pi to pi star transition is very high. That is, it means it is highly probable transition. It is highly probable transition. And why? So one thing that it requires not very high energy, it requires less energy for the transition of electron. And another thing that why it requires less energy for transition, one other thing is that this pi and pi molecular orbital and pi star molecular orbital, they lie in a same plane. That's why the excitation of electron or transition of electron is highly probable. So this is the reason that for pi to pi star transition, the molar absorptivity value is very high. Now next type of this transition, that is N to pi star transition. N to pi star transition. So for this N to pi star transition, where it is possible, they are possible in molecules having n electrons, or lone pair of electrons should be present, and it should also contain the double bond. So for example, this for carbonyl in carbonyl, where the carbonyl functional group is present, this transition is very much possible, or this C double bond N or C double bond S. So such type of transition is possible where this N electrons are there, where N electrons are present and this double bond is present and pi bond is present. There such type of transition is possible. So we may represent this one like this. Suppose if we have N electrons, then after taking energy, N to pi star transition is possible, and N electron which is present, the lone pair of electron which is present on this oxygen, it will go into the pi star region. Okay, anti-bonding pi anti-bonding orbital. So I may represent this one as, so only one electron is left over here, and another electron will go into the anti-bonding region. Suppose I can represent over here, this is the anti-bonding region. Okay, so or we can say, we can represent in this way. Suppose we have this sigma bond, and this is our p orbital which undergo sideways overlapping to form this pi bond. So this is our pi bond, and this is sigma bond, this is sigma bond. They will get overlap to get a pi bond, and two non-bonding electrons or lone pair of electrons which are shown over here. So they are, suppose I show it like this. So these are the two non-bonding or electrons present in the oxygen. Now one of the things, after this excitation, this electron will go into the anti-bonding region. So this will go into the anti-bonding region, and suppose this is now here two electrons are present like this. One electron over here, they will overlap and to form a pi bond. And now in this case we may represent two electrons over here and one electron over here. So one electron in this and another. So one of the electron from this anti-bonding non-bonding orbital will go into the anti-bonding region. So here, see, the electron is going into the suppose this is the anti-bonding region, because corresponding to a bonding molecular orbital, there is also the anti-bonding molecular orbital. So suppose this is going into the anti-bonding molecular orbital, one of the electron get excited into the anti-bonding molecular orbital. Okay, now so what is the one of the question may arise over here, that this for N to pi star transition, so no doubt this N to pi star transition energy is very less. Energy required is very less. Where is very less. And why the energy required is very less? Because N electrons are loosely held electron. Because N electrons are loosely held electron. On other side, for this N to pi star transition, the epsilon naught value is very low. Here for pi to pi star transition, what I told you, the epsilon naught value is high, but for this epsilon naught value is very low. So the reason for this is that, what I told you, the non-bonding molecular orbital is perpendicular to the pi star orbital. So if they are, means they are in different plane. That's why excitation is not easy. Though this occurs. Why it occurs? Because after absorbing the energy, there is some vibration takes place between this. The molecule, within the molecule, and there is a chance of partial overlap between this non-bonding orbital and pi star orbital. So that's why though it is less probable, it is as though the epsilon naught value is less, but the transition takes place. So sigma or epsilon naught value is very low. Why? Because a non-bonding orbital is perpendicular to pi star orbital, pi star antibonding orbital. So that's why transition is not possible. So why? But it is less probable transition occur. So what is the reason that transition occur though it is less probable? Because due to vibration, the partial overlap between these two orbital is possible. So transition occur because due to vibration between the molecule, within the molecule, vibration within the molecule cause partial overlap of the orbital orbitals. So due to this partial overlap of the orbitals, due to this partial overlap, the transition is possible, though it is not so much probable. So these are the different types of electronic transitions, and now in my next lecture I will discuss the selection rule for these electronic transitions. Thank you.